welcome to visualization using ChimeraX. Okay, so we continue with visualization using ChimeraX. So don't bother, my home screen is a bit messed up because I do a lot of work here. Yeah, but you can toggle that here, so just get a blank screen. So the first and most important thing is the help section. You can see a user guide, a quick start. Most of these are links that take you outside of the tool. It takes you to the browser, and then you can see a lot of things. So, for example, it pops up a browser where you can learn a lot of things about ChimeraX. Yeah. Okay. And we've already shown how to install them and all that. Okay, so what are the key things to know? First of all, when you come to Chimera, and then you can also might just want to launch the command line interface so that it's here in case you want to run some commands. And it depends on your version. I think this was one of the earliest version of ChimeraX. Yours might be more advanced than mine if you download today and install it. Yeah, but it's basically something. So we'll start by fetching a molecule. So it's connected to the protein data bank. You can fetch by ID. See so many things you can do from AlphaFold database, from PubChem, from Uniports, from everywhere. So you can fetch by PDB ID. Or you can just type fetch here. So want to fetch 3DGA. Okay. 3DGA fetch. Okay, I don't know why it's wrong, but let's see. It might just be a problem. 3DGA. Yeah, we are correct. So I don't know why the command line is acting up. Okay, so this is 3DGA. It's made up of so many chains, I think up to 4 chains. So we are going to just go through the process again, clean it up, select only one chain to work with, and then show how you can work around the chain, visualizations, and everything around. So let's go with action, and then first of all deal with color. So if you click all options, you can navigate around your color. So we'll start from background, and then want it to be white so that everything will make a lot of sense. So you can still, you might as well choose any kind of background that you are interested in, but I always think white is very, 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 very okay. Next thing is we are going to select, we want to only retain SA chain A. So if you select chain A, you invert every other selection so that you select everything that is not chain A, and then we can use atom and bond delete. Everything else goes out. So if you're using a mouse, so usually the right click, you can use it to rotate the protein. The left click translate the protein, the center button to translate the protein. So that's usually, but I think this can be reset. Yeah, this can be reset. Okay, just a minute. Yeah, so you have your toolbar. If you go to tools, you can toggle your toolbar. You can also toggle your log, and then our log is going to be somewhere here. So you can toggle your log, and then you can also toggle our model. Yeah, I don't know why mine is hiding. Yeah, okay. I think it's better now. Yes. Okay. So you can toggle some of these options. So if anyone you want, you can remove this. I can also toggle out the model. You can bring it back. So All right, so we are just dealing with only one. That's why it's showing only one model here. Fine. So this our protein that has a ligand. What do we do with it? So we also have so many other cofactors. If you check select and look at residues, you're going to see water. So you see a few water molecules are selected. So we'll also want to delete those. If you check again, you are going to see NDP, which is some co-crystal ligand, cofactors. And then we want to delete that. So at the end of the day, we are left with only the native ligand, which is this. So these are native ligand in the active site. So what can we do to this native ligand? We can change the representations, right? So we can look at action, atom and bond. It's already shown. If you click hide, it's going to disappear. Just select it, it's going to disappear. So we can bring it back by show. And then, yeah, then maybe we want to represent this in surface. So it shows the surface. So it's going to show the surface of the ligand. Yeah, and we can change the coloring of the surface. So first of all, let's deal with the transparency because now it has occluded our ligand. So we might want to look at transparency 70%. So we can see our ligand. Then we can also change the coloring of the surface here and make it maybe cyan. Yeah, I'll still deal with the transparency or maybe cornflower blue. And then I would deal with the transparency again, 70%. So this is what we have. You might as well even make it a mesh instead of solid, right? Yeah. Or maybe you can even make it a dot, just like a cloud, right? So you can deal with it whatever you want. Now, this our ligand is selected. So we can also change the color of the ligand. So here we want to deal with the ligand is atoms and bond. So you select atoms and bond, and then we might want to change the color. Or want it to be magenta, then color it by heteroatom. You can also color by elements. So different vector representation. Yes. So we can color by heteroatom, can color by elements, and what have you. Okay, so this is how we can represent our ligand. Yes. So let's deal with this whole protein now, right? So we can hold your control down, click on any part of the protein, then up arrow, select virtually every other thing in the protein. Okay, and then we can decide to change the color now because the protein is a cartoon. We want to select cartoon here and then change the color of the protein. Well, I want to also add that the protein is in cartoon, but some of the residues also are represented in sticks. You can see some of the residues that have the side chain in sticks. So this coloring will not appear to those residues unless I also select atoms and bond because those residues are out in atoms and bond, right? Okay, so usually I want to also give the protein a white color. Yes, so this is usually what I do. Everything becomes white this way. Then I can color whatever I want to color. So this particular residue now, residue 55. So we can select here, select one. So it's model 1, residue 55. Yes. So selected it here. So look at where I got my one. The ID is 1, so it's model 1. Then it's 55 is here. I can now choose, maybe I want to hide the atoms and bond. So you see it goes out, or I want to show it, it comes out. Then I can decide, oh, let me give it its color. Give it maybe a cyan color, then color by heteroatoms, something like this, right? So this is what you do to make it, a bit fine. Yeah, yeah. You can also choose any other residue of interest and keep coloring them until you get what you want. Maybe this forest green by heteroatom. It doesn't have a heteroatom because it's a phenylalanine. So this is exactly what you do in the active site to design it and make it beautiful or presentable. If you need more colors, you can actually click here to bring out the whole color palette. For example, this ligand, I might decide that, oh, I really prefer the color to be gold or maybe orange, then by heteroatom, and then I have it. Yes. So, sorry, and I have it here. You see, I'm beginning to make my active site look very, 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 very interesting. So you can zoom in to what you want. Okay, so that is it. The whole protein too can be represented in, I mean, in surfaces, right? So I can decide to also choose select the protein. Yeah. Then I will go and say, oh, sorry, action, surface, show. Then my whole protein is in surface. I can also decide to deal with the transparency or make it 60%. Then you can see the surface. You can see where my ligand is. You can see the residues that are flanking them. And so many things can happen here. Many things are possible. You see the clefts where the ligand can diffuse into the active site. So you can make all these representations very possible. Yeah, and you can as well, um, you know, hide the hide the surfaces when you don't need it again. Okay, so this is one. The next thing is, how do you calculate distances, angles, or maybe torsion here in the in your protein? I mean, between residues or between atoms. So, for example, we might decide I want to know the distance between this fluorine molecule. Sorry, this actually, yeah. So this compound, this atom here, and this other atom here, right? Or we might actually decide to check the distance between one of this nitrogen here for this arginine, sorry, this guanidine side chain, or this guanidine part of the molecule, and this methionine. So if I select the two, I can look at tools and look at structural analysis and check my distances. So I've selected two atoms. Distances require just two atoms. I can now ask it to create a distance for me. So it's going to tell me, oh, it's 6.079 Armstrong. I can play around the color. Yeah, can play around the color, or maybe possible how many dashes, or maybe number of thickness of the dashes and everything. So this is how you add distances. You can also compute angles by specifying at least three um, angles and torsions or whatever you have, can specify up to three atoms to be able to compute angles and then also torsions. So if I specify three atoms like this, so if I decide, I can also specify this, and then I can create sorry, yeah, yes, I can create an angle, and the angle between this atom, nitrogen, this carbon, and here, this other carbon is some 3.7 degrees. So that's angle. So for torsion, you need four points. You know how it works. Angles, 3 points, torsion, 4 points. You can even compute a plane, can define a plane between at least 3 points. Yeah, can define a plane between 3 points, especially when you measure geometry or measure dihedrals and torsions. You can define a plane. You can color it with whatever color you want. Yeah. So these are the things that are possible when dealing with can also delete the okay. Yeah. So once you are done this way, what are other things that are available to you? Let's assume, oh, I've depicted the structure I want, I've calculated the distance that is most important to me, and I can see the distance. What do I now do? So I will need to maybe rotate this until it comes very close to what I want. I mean, the representation, the side I want to see, and everything. So let's assume this is fine for me. Right, so we're going to assume this is fine for me. Okay, and then I will go ahead and save this out. File, save. So usually you select, oh, image TIF is fine. I think there is also PNG. I am not sure again. Yeah, but TIF image is fine. You can select the image and then decide to save this out. So usually you might be interested in saving it out in a known folder instead of saving it in general ChimeraX folder. So I might just give it whatever name, test, yeah, test that image and then save it out. It looks like, yeah, so you can see very high resolution image of your active site. So that's actually how to use ChimeraX. So there are a lot of functions here. For example, you can take snapshots of whatever is happening on your desktop. So these are dealing with your atoms. Let me remove this surface. Yeah. So if you are dealing with your atoms, you can also toggle this. If you are dealing with your proteins, you can also toggle this. And then, yeah, so this is also board representation of your atoms. So, and then you can also space field, I mean, van der Waals presentation. So these are also things that are available and possible depending on what you want. It might not be necessary. Yeah, but as you work, you keep defining how you want to represent your structures or your visualization and everything. So that is that. For molecule display, there are still a lot more options available. For example, this is differential coloring. Yeah, this is a very differential coloring, and then on and on and on. There are many options that are available. For example, here, detect hydrogen bonding. It has detected a lot of hydrogen bonding between my molecule and the protein, both intramolecular bonding and intermolecular bonding first. So for example, you can see bonding between this nitrogen and this. Then you can see bonding between the molecule and other parts of the protein. So these are things that are possible in ChimeraX, producing high quality images, especially for publications. Yeah. Let's talk about how to use Pymol for visualization. Yeah, so Pymol is a great tool for visualization, and As I mentioned during the tutorial, I told you you can install it even though you don't have a license. As you can see here, they always tag me, no license file for evaluation only. So all images I produce here carry that watermark. Yeah. So you have to know that beforehand unless you go and purchase license from Schrodinger. Okay, so when you open when you open Pymol, sorry, then you can, there's so many options. I mean, get your PDB, you can open a structure and all that. Also here, there's an option to change the kind of button you are using. Yeah, is in the editing mode or is in the viewing mode and all that. So, I mean, the controls on your mouse. Yeah, and then so many other things. Yeah, so there are many options available in Pymol. For example, the wizard, you can do mutagenesis. We talked about mutation and all that. You can even build fragments, residue, whatever. Now, but our goal in this tutorial is visualization, high quality images in Pymol. Now, for that, I prefer using a script because Pymol is designed so that I just write plain language scripting that is wrapped around Python and command line interfaces. As you can see here on my right, I have a lot of script, and this is exactly what we're going to try to implement, right? Yeah, so usually if you have a structure you want, so you write the scripts carefully. Once you are done, you can run it at once and just see everything that happened to your structure. Yeah, so that's exactly what I recommend in Pymol. And then especially also maybe if you have a series, maybe you have a particular protein that you docked against 5 ligands and you want to visualize them. Since it's the same protein, you can build exactly the same kind of script and apply to each of them, and each of them will bring out similar kind of beautiful structures. So that's what I recommend. So we're going to do it now. We're going to start with reinitialize. Initialize is just to bring the Pymol into the normal, as if you started it afresh. You understand? So as if you opened it. So reinitialize just brings it this way, and then the second thing we want to do is to make sure if you're working on Pymol, you want to know where your directory is. So if you see here, you can see working directory, you can change your directory and what have you. So we can also deal with it here. Print working directory is telling me, oh, I'm somewhere in documents, so I can change directory into downloads. So if I print working directory again, I'm not, so depending on where you want to save your, but you mustn't change directory. When you start saving your images or your protein, whatever, you can specify the directory. But it's also necessary because if you're using the command line to load a protein, you must specify the right path to where the protein is. So first of all, we want to load this protein now because this protein, I couldn't find it in my laptop. We're going to fetch it directly from PDB. So I'm going to run fetch for EIY. So we name it protein. So we have fetched this from PDB. So as you can see, yeah. So second thing, we need the background to be white. This is now good. So if you check one of my code, you are going to see BG white. So that's exactly what we do here. BG white, background white. Sorry, I didn't get the white spelling of the white. Yeah, so my background is now white, so I can see everything clearly. Right. So depending on what you want to do, you can go ahead to start selecting. So now, because the goal of this script is for us to visualize the hydrogen bonding that this particular ligand makes, or how hydrogen bonding contact it makes with the protein, right? So because of that, first of all, what is the name of this ligand? Where is this ligand coded as? So if you click on any of the atom of the ligand, you can see it's named ZMA, just like it's written here. So we want to select that ligand so we're going to run this code here, select ligand. So that's the name we're going to give it, ligand. Chain A, you see it's chain A, and rest name, that is residue name, ZMA. So you see, it has added selection. So I forgot to say that everything you start selecting, it starts keeping them here. The protein, the ligand, so we can see selected ligand. Now, we just selected ligand because that is the most important thing for us. So we can hide everything and start loading things one by one. That's just something beautiful about Pymol. So once you've defined your selection, you now can find everything and start loading them one by one. Let us also define one other selection. It's not in my code, but let's define the zinc selection too. I think there is a zinc ion here. No, it's actually a sodium. So let's select ion as a chain A and rest name sodium. So that is the ion. So we can then hide everything and then start loading them sequentially. And that's the beautiful. So we hide everything or hide all. So we now start select environment with residues, everything. So I'm going to just run this whole code. So it brings back my ligand with the residues that are surrounding it, not just everything in the protein and all the distances associated with it. So as you can see here, my ligand is here. So we're going to change it. Change the coloring of the ligand so that you see what it works like. So let's hide labels. Hide labels, H bond. So we have hidden the labels, all the 5 Armstrong or 3 Armstrong and everything. So even though the co-crystallized waters are still available, so intra-residue, intraprotein, H bonding interactions are also available. Okay, so now set dash gap. We set dash gap to 0.4 just to make it thinner, and then dash radius, dash lines, whatever. So let's just run all these commands. So it has even become a little bit smaller, as you can see. So now to differentiate our ligand, because if you are looking now, it's only me, or if you are very careful, you can see our ligand. But to differentiate that, we are going to color our ligand separately. That is the next line. Color gold, element C, and ligand. So you can see we have colored our ligand with heteroatom numbering. You can see it's retained all the heteroatom numbering, as you can see here. Yeah. So then the environment, we are going to color it gray. So it's not green. I'm going to color it gray. Yeah. So you can see it's becoming beautiful. So we can now restore the full protein cartoon, but at a very high transparency. At a very high transparency so that it fades into the background. Yeah. So we are getting there. You see, we are getting there. You can see our ligand hiding within these residues. And then you can even see the cartoon at very, very low transparency. And then you can finally orient the ligand so that you bring it to focus. Yeah. So this is basically a walkthrough on how to, create a very, very good visualization. And the funny thing is this, I just ran it, from series of code, and it can be reproduced. I can just give you the script again. You even know the protein ID, and you can reproduce this exactly by running those commands. And that's what I advise, because if I'm clicking here, I have forgotten the first things I clicked before now. So you can also even reduce the size of this environment. I mean, the size of these residues that are in the environment. You can reduce them so that the ligand stand out. Stand out in a clearer way. Yes. So this place that we run. Sorry. So this place that we run color gray 70, element C, and environment. So we can actually set the size of the environment. Yeah, we can reduce the size of the environment so that it becomes a bit it becomes a bit less thick, and then our ligand become pronounced. Yeah. So these are the things that happens. So you can say our ligand, can see the key interactions, and then we can set it anyhow we want. And then once we are done, we can save it out. Yeah. So we can save this out by running PNG. We'll give it a name. H bond interact dot PNG DPI equals to 500. So and then before I run this, let me once again confirm my working directory. So this is in downloads. Alright, so I think I can run it, and then it's saved. So if I check my downloads, I'm going to see it. So very, very high quality, high resolution image that's available for us. You can annotate them and then use it. So this is what I recommend. So this is what I recommend when dealing with visualization in Pymol. Yeah. So whether you're working with a protein alone or whatever, you see them and generate the code. I mean, the script on how to use it, and then once you run it, it's like a magic and it happens. All right. So there are many more scripts, maybe, but I'm going to make this particular script available in the module so that you can also run and reproduce the same thing. Yeah, thank you. I'll be showing you how to use Discovery Studio for visualization, especially if you're working on protein ligand interactions. So I'm just going to show you part of the tutorial from the docking section where I use Discovery Studio to visualize interaction between a duct ligand and a protein. So in Discovery Studio, I'm going to open that. Yeah, so I'm going to open this. Yes. So don't worry, this is the representation. This is just the representation. So I'm going to change that. So first of all, let's set our background color. It's dark, that's not good. So I'm going to make it white. So I'm just going to choose good display. Yeah. So as you can see our protein and our ligand together as one complex, right, in the active site. So how do we see the interactions that are happening here? That is important to us, right? Let's look at the interactions that are happening between the ligand and the protein. So we're going to look at ligand interactions. So once we click ligand interactions, yeah, so we can see this. Okay, yeah, remember in display style, you can choose, so many different ways to display this. So we can see all the possible interactions, hydrogen bonding, these ones that are green. Obviously, we're just going to put that up very soon. We can see pi to pi, we can see pi stacking, pi alkyl interactions, and so on. So first thing, we are going to label these residues. So we want to know which residues are making these interactions. So we're going to create labels, and then our labels, we want it to be on amino acid, and then we want the name to be 3-letter ID. Yeah, 3-letter and ID. I think it's fine. I want to also make this very bold, maybe 28, and probably choose a very cool color and say apply. The color, the thickness is not good. Okay, good. So we can see all the residues that are interacting with our ligand of interest. We can see which ones form hydrogen bonding, which ones phenylalanine with pi-to-pi stack interactions, and so on and so forth. So these are the things that we can easily visualize. So we can also look at a 2D diagram of what is happening here. If you don't want to see the 3D, you can look at the 2D diagram. The serine 108, isoleucine 164 is also having a hydrogen bonding with this tertiary it's a secondary amine group. Okay, so and then you can see the different type of interactions. As I mentioned initially, conventional hydrogen bonding is the green one. Then all the other colors, there are even some sulfur pi interactions, especially from the methionine and so on and so forth. So this is just a simple way to represent the interactions that you see in your complex. So if you toggle here, you are going to see a very, very different ways of representing the interactions between your ligand and your protein. So it's up to you. Usually, if you're preparing, publication quality interaction diagrams, so you usually fine tune them until you get what you want, and then you can export it as an image. Yeah, you can save it out as an image. Okay, so I think with this, we have seen that when you create the complex of your docked ligand with the protein, you can easily see what interactions. You can even see how is it situated in the active site and all that and all that. So that is it. All right.